So, okay, first, what's a non-local game? Let me just write down a formal definition of it, just so we know what we're talking about. What's a non-local game? You know, we saw an example of it, like the CHSH game or this Magic Square game. But in general, a non-local game is, it's a tuple of a bunch of things. Okay, so it's this long tuple. Where X, Y, they're finite sets. They represent the set of possible questions that you can send to Alice and Bob. So these are question sets. A and B are going to be answer sets. This mu is a distribution over questions from X and Y. And this D, it's what we call a decision predicate. So it sort of says, when do the players win this game? So it's a function from questions and answers to 0 or 1. So if you want to know whether the players won this particular game, you just plug in the questions that they received and the answers that they reported, and this D function will tell you whether they won or not. So we call this the decision predicate, or just decision procedure. So that's what a non-local game is. And suppose someone came up to you and said, here's my favorite non-local game. Here are the rules, here are the question distribution. What is their maximum probability of success? Can you compute it for me? Is there an algorithm to do so? And as we mentioned a couple weeks ago, turns out the eventual answer is there actually is no algorithm to do this. And today we'll start to see, like, how do you prove such a thing? So you have a game, and well, we should say, what does it mean? Like, what does it mean how do you measure this optimal winning probability? So you have to talk about the types of strategies that the players are allowed to use. We're going to talk about quantum strategies because that's what we're interested in. But there's different kinds. So here's a definition of a quantum strategy. So I'll say a finite dimensional strategy for a non-local game. G, it's going to be, you get to pick a shared entangled state between Alice and Bob and measurement operators that they'll use. So it's going to be a choice of state psi and measurement operators. Right, so since we're just focusing on finite dimensional strategies, this state psi is going to be in the tensor product of CD tensor CD for some finite D. And then these measurements, they're going to be some choice of D-dimensional positive operators that sum to identity, yada, yada, yada. Okay. So if Alice and Bob decide to use such a strategy, what is their success probability? So I'll say that it's going to be omega of this game G, and you fix this particular strategy So what is it? Well, you say, I'm going to choose the questions X and Y at random from this question distribution. And then I'm going to sum over all possible answers that they could produce that would lead them to win the game. So you say, I only care about the A's and B's that have them win. And then you have to put in the probability that when they perform their measurements, they actually generate this particular A and B. So that's given by this expectation value. Okay. So hopefully that should make sense. Now, we can define the quantum value to be this omega star of G, and we've seen this before. This is going to be the supremum over all finite dimensional strategies S of their success probability given that strategy. So we call this the quantum value of the game. So measures how well they can do if they use a finite number of qubits in their strategy. All right. So the complexity question was, or the computational problem is, given G, estimate omega star G, say plus or minus, some small constant like 10%. Can you come up with an algorithm to do that? Turns out no algorithm. So I mentioned last time that, okay, so that itself is already pretty interesting. But there's more to be said because it's actually connected to seemingly unrelated questions in other areas. So the last time we left off with, there are connections to, say, mathematical physics. And there the question is,
yeah, sorry. Can you remind us if that's a proven result, the fact that there's no algorithm?
Yes. So this is a proven result, and we're going to see at least a high level of what goes on into this proof. Yeah. So I think last time someone, I forget who asked, but someone asked, is it that we don't know of an algorithm, or we know that there is no algorithm? And it's the second thing. We know for sure that there cannot be an algorithm. Okay, so what are these other connections? And last time we had this very interesting, discussion about finite dimensional versus infinite dimensional entanglement, and whether nature can be described, using finite dimensions only, or is it inherently infinite dimensional? So this complexity question gets into that. So here the question is, at the start, not about complexity theory or anything. It's just saying, can nature be described using a finite dimensional theory? Or is it inherently infinite dimensional? Right. And, I guess if you take like a, standard quantum mechanics class or something, a lot of things are presented naturally in infinite dimensions, right? Like the Hamiltonian describing a hydrogen atom, it's infinite, it acts on an infinite dimensional space, right? And so you might think actually maybe it's inherent. On the other hand, like if you're coming at things from like the quantum information theory point of view, everything's taught in terms of finite dimensional Hilbert spaces, right? So, you know, what's the more appropriate model of nature? I guess this, you know, this can get like quite philosophical, and maybe it's, you know, I don't think we're anywhere close to resolving this. But there's actually a really precise way in which we can get some angle on this question and actually come up with a precise mathematical answer to it. So we'll instantiate this question by asking, you know, in the context of non-local games, does it make a difference if Alice and Bob are allowed to use infinite dimensional quantum states and quantum strategies? Right? Does this infinite dimensionality offer them any advantage? Right? So this is a very well-defined question, and you can hope to answer it. Right, so that's the question we'll look at. And I should define, like, well, how do we model infinite dimensional strategies? And last time we talked about a couple models. The most straightforward generalization to infinite dimensions would be, well, instead of this quantum state psi being in CD tensor CD, why don't I let it be in H tensor H for some infinite dimensional H? I mean, this is fine. This, you know, you can talk about such things, but it turns out that this model can actually, it doesn't give you any additional power on top of finite dimensional strategies, at least in terms of non-local games. You know, whatever infinite dimensional strategy they use in this form, they can approximate it arbitrarily well using a finite dimensional strategy. Okay, so this generalization is maybe not so interesting. But there's another generalization called the commuting operator model, which you can say more things about. So this is how we model infinite dimensional strategies. So you choose a state. You know, you have measurement operators as usual. So this state, all you say is that it's just a vector in some Hilbert space. Okay, this Hilbert space doesn't necessarily have any tensor product structure. It can be finite dimensional, it can be infinite dimensional. These operators, they're measurement operators. They all act on the same space. But in order to make things like, you know, in the setting of non-local games, we have this constraint that Alice and Bob can't talk to each other, right? Like they cannot, you know, they get an input, they get a question, and you know they don't know what the other person's question is. So you need to install that into the definition somehow, and that's from the constraint that their measurement operators commute. And what that means is, you know, Alice and Bob, they're going to measure the state psi and they're measuring in the same space. But since their operators commute, it doesn't matter which order they measure in. Like Alice can measure first, Bob can measure first. The statistics of their outcomes will always be the same. And what that means is they can't do anything to like send the signal to the other person. Okay. Any questions about the definition of a commuting operator strategy? So, if they decide to use this kind of strategy, then how do you measure their success? Well, it's largely the same. You just omit the tensor product signs, right? Because there's no such thing as a tensor product. Right? We just have the same expression. Right, this is the probability that they win. Right, so here, instead of tensoring the operators together, you just multiply them. But again, the order in which you multiply them doesn't matter. And so if we allow ourselves to maximize over these kinds of more general strategies, we call this the commuting operator value of a game. And so this is the supremum over commuting operator S of omega G comma S. So this is a different kind of value. And one easy thing to see is that the finite dimensional value, or this quantum value that we defined before, is always at most the commuting operator value. And this is because the commuting operator strategies are just a strict generalization of finite dimensional ones. Right? Like, because you could have imagined that, this Hilbert space H here was actually a tensor product of two spaces, Alice's space, tensor Bob's space. And then their operators is, if you look at it closely, it really looks like, some operator on Alice's side, tensor the identity. And then for Bob's measurements, it's identity on Alice's side, tensor some operator on Bob's side, right? And clearly, Alice's and Bob's operators will commute.
What is W star?
The omega star here?
Yeah, omega star, yeah.
That's the finite dimensional value, or the quantum value. It's their maximum success probability when they only restrict to finite dimensional strategies.
But that's the quantum one, right?
Yeah.
Okay.
I guess it's maybe a little ambiguous when I say quantum, because you could also say that the commuting operator thing is also quantum. I guess it's just like it's just a naming that's stuck. Yeah, actually, maybe just to make things clear, we'll just say finite dimensional value versus the commuting operator value, just to make things perfectly clear. So we know this fact, and this holds for any game you walk up with. But the more interesting question is there a game G such that there's actually a difference between these two values, between the finite dimensional value and the commuting operator value. Right. So if that were the case, then it would mean that in this game G, if Alice and Bob decided to use this more general commuting operator strategy, they would be able to achieve a higher winning probability. So it actually benefits them. And actually, in that case, it's, not only is this, better strategy, a commuting operator strategy, it has to be infinite dimensional. And the reason that's the case is if you restrict yourselves to finite dimensions, then, well, I guess it's by, oh, right. So, the point is, if you're in the commuting operator realm, right, there's no notion of tensor product, but you say that the Hilbert space is finite dimensional, then in fact, it turns out that you can actually find a tensor product decomposition of your space. Right, so just to write it down. So, I won't show this here, like this is some, I guess, some result in functional analysis, but it's true. If you're in finite dimensions, there's no distinction between tensor product spaces and commuting operator strategies. So if there is a difference, that's this question, then it must be because there's an inherent advantage or inherent difference between finite and infinite dimensions. So one of the things we mentioned last time is that, suppose there was such a separating game, right? A game where finite dimensional and commuting operator value were different, then this game would be in principle some kind of experimental test of infinite dimensionality, right? Like, imagine you're playing this game with your lab equipment, and then you see that the winning probability is tending closer to this omega co value rather than the omega star value. Then that suggests that whatever nature is doing inside your lab equipment, it cannot be described using a finite dimensional strategy. Okay, so this question is known as Cyrilson's problem. Right, this is named after the same Cyrilson who came up with, who proved that CHSH, you can't do better than this 85% number. And it's not an easy question. Like all the non-local games that we saw so far, CHSH, Magic Square, and so on, none of these exhibit a separation between the finite dimensional and infinite dimensional values. So, the omega star of this CHSH, right, which we saw was, this 85.4% value, it's the same as the commuting operator value. Same thing with Magic Square. Um, okay, so that's the mathematical physics question. Here's where it connects back to this complexity, right? I mentioned that this question of, is there an algorithm to estimate the value, this omega star value of a game, somehow connected to this finite versus infinite dimensions? It comes through the following. A different color. So if it were the case, imagine that we were in a world where if no matter what game you came up with, there was no difference between these two values. Not only would it say that, okay, infinite dimensional strategies don't help you at all, this would have the interesting consequence of giving us an algorithm for estimating the quantum value of a game. Right, which is the thing we were wondering about in the beginning. So, how does this work? Well, it's because we can actually combine two different semi-algorithms, so one semi-algorithm, and I'll explain what that means in a minute, will approximate this finite dimensional value from below. And the other semi-algorithm will approximate this commuting operator value from above. And since if we're assuming that they're always the same, then these two semi-algorithms will actually converge to the correct quantum value. So the first semi-algorithm, let's call it search from below. So what does it do? Well, it's an algorithm that it just computes this sequence, this infinite sequence of numbers, alpha 1, alpha 2, ... And it's just going to keep computing them. And what's an alpha? So alpha D is going to be the best winning probability so we're fixing some non-local game G here, right? We fix it ahead of time using a D-dimensional strategy. So if you remember from our discussion from last time, if you fix the dimension of the strategy you're considering, then this alpha D, you can actually approximate it, right? Because you can discretize the space of the strategy. And it turns out that there's only like a finite number of possibilities you need to consider. So you can, in the worst case, enumerate over all of them and just pick the best strategy. So this alpha D, it's computable in some finite amount of time. So for any given D, you can just compute it. Clearly, these alphas form a non-decreasing sequence, right? Like if you increase the dimension of strategy that you allow the players, they can't do any worse. The other thing we know about this alpha D is that in the limit, as D goes to infinity, it will approach this omega star value, right? So all of these are lower bounds on omega star, and they will eventually converge there. The issue is that we just don't know how fast. right? And that's a major problem because you're running this algorithm and you just don't know when to stop the algorithm because you don't know if you're any closer to, if you're at all close to the true answer. So that's why I call it a semi-algorithm. Like you can just run it forever and it, we just know that in the limit, it gets closer and closer to the correct answer. All right, so hopefully this rings a bell. The other semi-algorithm is what I'll call search from above. And it also computes an infinite sequence of numbers. So it computes beta 1, beta 2, so on. But this time, these numbers are, they're non-increasing. They're slowly getting smaller and smaller. They're all going to be upper bounds on this commuting operator value. Okay. What is this beta d? Well, it gets a little more technical to state, but it's some quantity that's computed from some convex optimization problem. And the point is that they're all just guaranteed to be upper bounds on this commuting operator value. If you're really curious what it is, it's the best, or this is
like
this.
It's some solution to an SDP relaxation. Yes,
exactly. Yeah. So if you know what an SDP relaxation is, then that's what it is. It's the smallest number such that beta d minus your target value, this omega co. The fact that this is non-negative is certifiable using degree d sum of squares polynomials. Okay, whatever this is. The important thing is that if you plug in, you fix a d, you can write a program to compute this number. In fact, there are even packages you can download online that will do this sort of thing. Right, this is.
What did you say they were called? Yeah, okay.
Which thing was called?
Yeah, the beta Ds, or the solution. I don't know. Someone said some technical term that I was going to Google, but I don't remember what it was. Like, what are these beta Ds?
Oh, well, it's sort of what I wrote. It's like the smallest. It's basically the solution to a semi-definite program. And a specific semi-definite program, and if you wanted to Google it, you can look up this thing called the NPA hierarchy. And there is software that people have written that actually implement this convex program. But for this discussion, we don't necessarily care exactly what the definition is. This is so you can compute this in finite time, and beta d will converge to omega co as d goes to infinity. Right. So and again, we just don't know how fast it converges. So you probably see where this is going, right? Like we can put these two things together. Imagine that we have this, someone hands you a non-local game. It has some true quantum value, right, that we're trying to estimate. And we're assuming that, suppose it's the same as its commuting operator value. And we can compute from both sides these alpha d's. Right, so d is going to infinity. We can also compute these beta d's. Since they're both guaranteed to converge, we know at some point they're going to get within epsilon of each other, in which case your algorithm knows, aha, I've homed in on the correct value.
So you said before that we know this doesn't exist, right? The estimating algorithm?
In general, yeah. Sorry, give me one sec. Right, so so in this, if this happens, then we know we've converged to this value, and then that's it. You've estimated this omega star, right? So I've presented you an algorithm that works if under this assumption that these two values are the same for all G.
So in other words, then, an algorithm to calculate the winning probability exists if and only if for all G, these numbers are the same. And the algorithm doesn't exist even if you're applying it when they are the same, unless all G obey this property.
Oh, not that strong. So this is a fact. If they are the same, then this algorithm that I just described, like this algorithm you can even code up today, it will work. I mean, it'll take forever, but it will work. But if for any game for which they are not the same, then your algorithm will just spin its wheels, and these two sequences will not converge. And you were just wondering, wait, is it going to converge at some point, or are they really different?
Right, which is what lands it in the uncomputable class.
Yeah, exactly. So okay, so right. So really now this question of, so we've tied the two questions. Whether infinite dimensional strategies help or not is directly tied to whether there's an algorithm to approximating this this game, maximum success probability, right? So that's one connection. Any other questions about this link?
Yeah, sorry, can you hear me? It's a little bit glitchy on my end.
Yeah, can hear you.
Am I jumping ahead a bit since you said that it's been proven that there's no algorithm that can do this? And now you're saying there is an algorithm if they're equal, then they're not equal? Is that where we're going?
Yeah, exactly. Right, so that is the correct implication. So we're going to show that there is no algorithm for estimating omega star. So in particular, the algorithm I just described cannot work for all games G, which tells you there must be some game out there, don't know what, but some game where they are different, there is this difference.
Wouldn't that by itself indicate that our earlier question about whether we need infinite dimensional spaces to model the world, wouldn't that say yes, we do?
I guess it would. I would view it as it still leaves open the possibility that you need infinite dimensional spaces, because if there is a separating game, it's not clear at all that this game is experimentally realizable in our universe. It just says that at least mathematically, it's not ruled out.
So this is the solution to Sirelson's problem, but we just don't, like, we haven't found an actual game that does it, but like we know the answer.
So yeah, we know the answer. In fact, we do know of the game. Like, we can write down a description of the game, but it's still very mysterious. Like, the description of the game is very opaque. Like, it doesn't tell us anything about what this. So this game we know for sure. Like, I can write it down, and this, I know this game has infinite dimensions. Help, you can do better using infinite dimensional strategies, but we have no idea what this infinite dimensional strategy looks like. We just know there's a gap. But I'll say more about this later.
So it's a game that then no one has ever won.
At least no one has ever won with the mathematically allowed maximum probability. What am I even saying? No one's ever played this game. Like, it's only been written down, like, theoretically.
Right. Is there any notion of playability in a non-local game? Like, are we sure that just because we've described a valid non-local game, we've still described something that could be done? Even getting rid of, like, technological limitations.
Oh, I mean, I don't know how you would separate out whether something's done versus technological limitations. At least to me, they seem like the same thing.
Well, I mean, there are cases where they aren't the same thing, right? Like, if a game required you to do some faster than light speed travel, or to manipulate, 3 qubits each maximally entangled with each other, you would have an unplayable game. Is there something in the lexicon of these games that already forbids other
I see what you're asking. I'll say this. I guess this game, it's formulated within the mathematical framework of quantum field theory. So, okay, well, there's a couple things. Like, one is that apparently there's still no well-defined mathematical, like, rigorously formalized mathematical framework for quantum field theory. This is actually, people are trying to figure this out. But at least people agree on some basic axioms. And this game is compatible with those axioms. So as far as we can tell, it's compatible with what we believe is allowable by quantum field theory. But the question is whether, all these, whether you need more than just these bare axioms that people have listed. Yeah, so where am I going with this? Yeah, I don't know. Hopefully that kind of answers your question, maybe. So just concretely, like, you're not allowed, it won't allow you to, like, manipulate 3 qubits that are maximally entangled, because that violates the axioms of basic quantum mechanics. So that's not something that happens here.
All right, that does help.
Okay, so this is connection with finite versus infinite, and now let me just quickly mention this connection with this area of pure math. So the Sirelson's problem turns out to be equivalent, and people only discovered this like 10 years ago. It's equivalent to something known as this Connes Embedding Problem. This is a problem that was formulated in the 1970s in this area of functional analysis called operator algebras. Okay, you know, I know basically nothing about operator algebras, but at least I can try to convey what I think is a sort of a cartoon picture of what this Connes embedding problem is about. Like if you look up the Wikipedia article on this embedding problem, you know, it's just like a lot of words that, yeah, at least I've never heard of. But let me, you know, I think I have some cartoon explanation of it. So it's about something called von Neumann algebras. What's a von Neumann algebra? It's basically some abstract set of operators acting on a Hilbert space. Okay, so it's a set of operators acting on some Hilbert space H. Okay, generally people really like the H's that are infinite dimensional. Those are the most exciting ones for the mathematicians. Also, by the way, if someone in this, an audience, like you've taken a class, like feel free to jump in and save me. So it's a set of operators on H. Since it's an algebra, you can add and multiply them, and it all lives in this algebra, right? So you can imagine it's like this giant, infinite bucket of operators, and it also satisfies some closure properties. Okay, so it's this really abstract kind of thing. Multiplication also contains limit points, right? So I guess this is sort of the defining feature of a von Neumann algebra. Like if you take a sequence of these operators, the sequence will, if it has a limit in some appropriate notion, then this set will also contain that limit, right? So anyways, just that's how we can think of this von Neumann algebras. In this subject, people care a lot about classifying all the different types of von Neumann algebras out there, right? And it, it's really serious mathematical work to try to figure out like what are the different types. And this Connes embedding problem, the CEP, it asks whether there's a certain class of von Neumann algebras called type 2-1. Okay, so very scary looking nomenclature. So this is a certain class, whether they can all be embedded in a very specific von Neumann algebra, something that's very nice that we have a pretty good handle on. Okay, so technically speaking, it's not just embedded in this thing, but technically an ultra power, whatever that is, an ultra power of the hyperfinite algebra. Okay, so what's the significance of this? This hyperfinite thing, it's really nice because basically we can think of this as representing the algebra that is where you can approximate it using finite dimensional stuff. Okay, and you can maybe start to see why this would be really nice, right? Like, you have all these really abstract things in there, super crazy and infinite dimensional, but if it turns out they can all be viewed as, instantiations of this hyperfinite thing, then it says, well, all the tools, all we need to understand are just its finite dimensional approximations. And, I think we have a pretty good handle on finite dimensional matrices, right? They're very concrete and we have a good feeling for them. So mathematically, this would have been a very nice outcome. And this was a question that was asked in the 70s, whether this was true. And so this started off in operator algebras. And over time, people realized that it's actually something that goes beyond functional analysis. Like people discovered that there are equivalent formulations in group theory, in ergodic theory, and many other parts of mathematics. And it turns out that all of these questions are equivalent to each other, right? In maybe a surprising way. And all these questions all have the flavor of, can you approximate some infinite dimensional thing using a finite dimensional object? And one of these equivalent formulations was the serial problem, right? In quantum information theory, it turned out that it's equivalent to CEP. So that's kind of a very curious connection, and it's sort of like surprising and mind-bending that we started with something just about, is there an algorithm to do something, and it's now related to this very abstract, deep question in pure mathematics. And so I should say exactly what's the directionality of equivalency. So if CEP is true, then omega star is equal to omega co G for all G, right? In particular, this would, if CEP is true, then there is an algorithm for non-local games. Actually, so does anyone actually know what the von Neumann algebra is, or has taken like a class in this stuff? I know that there's some math students at some point. Oh, right. Randy, are you covering like this sort of stuff?
This is the prereq for the course that uses it.
Sorry, I didn't get that.
This is the prereq for the course.
Oh, it's a prereq for the course. Okay.
Hopefully taking it next term.
Okay, so yeah, maybe this is a good break point. Let's come back in, let's say 5 minutes, like 5:05, and we'll start to see how do you disprove the existence of this algorithm.
Hey, Henry, can I ask a question in the meanwhile?
Yeah, what's up?
So I'm a little confused. So wasn't Cyrilson's problem already implied by Slofstra's result? And so why did it take until the proof of MIP star equals RE to disprove CEP? I know something's off, right?
Yeah, good question. So actually, there's multiple Cyrilson's problems. And I think the Cyrilson problem that I'm mentioning was like the original one. But then over time, people came up with more fine-grained versions of them. And what Slofstra's result, what Slofstra did was he created a separation between two other correlation sets. So basically, he showed that there's a game that you can come up with where if you look at the sequence, the limit of all finite dimensional strategies, there's a particular limit, right? Like the winning in the limit, the winning probability is 1, but there is no finite dimensional strategy that actually achieves 1.
Right, and this is not the one that CEP is equivalent to?
No, so CEP would say that so here it doesn't insist that that there is something achieving the limit. So basically, this is saying that it's like the difference between a gapped result versus a non-gapped result. So if there is a difference between omega star and omega co, it would say that with commuting operator you can win with probability 1, but even if you take the limit of finite dimensional strategies, you'll get a limit that's strictly less than 1. Yeah,
Okay, there's a subtle difference then.
Yeah.
Right, so the other one is just, I guess, saying that for omega star, you need the supremum rather than like a maximum. But the result we're talking about now is saying that even if like you take a supremum, you still have this gap.
Mm-hmm. Yeah.
So can I come back to a question I asked earlier, which is, okay, we haven't proven the result, but if I'm understanding right, we have said that there is some game such that omega star is not equal to omega co, and I'm not like before you kind of hedged. When I asked like, why do we not take that as like a definitive answer to whether the world is needs to be modeled as infinite dimensional? Yeah, so like, can we take that as a definitive answer that yes, like we actually do need, infinite dimensions?
I'm still not sure. I mean, it's just like related to Sumner's question, like, maybe it's just not physically possible to play this game and achieve this omega co value, in which case, you could argue that maybe still you don't need.
Okay, but the only reason that would be the case if, once we say make QFT, rigorous would be because the game doesn't satisfy, some property of that final QFT. But supposing that it does, which I think is kind of what we should believe at the moment, then the answer to that question is yes. To the best of our knowledge, we need to model the world as infinite dimensional.
I guess it would tilt the needle more in the direction, at least, okay, my opinion, I think it would tilt the needle more in the direction of what you're saying, but you can still raise possible valid objections to whether, if there's a technological obstruction, like, let's say, I don't know, because of like, the configuration of like the only way to like conduct this experiment is if you collected so much mass in like a very compact area that it would like create a black hole or something. Maybe you'd say, okay, actually, maybe it's not feasible on physical grounds. Yeah.
Fair enough. Thanks.
Okay, so let's continue. So let's jump in to see like how is this non-computability result proved? So this is the content of this result MIP star equals RE. And the main statement of the result is that there exists a computable reduction or transformation from Turing machines M to a non-local game G sub M such that if M halts, then the omega star value of this game is 1. If M does not halt, then the omega star value of this game is at most a half. So a Turing machine, you can just think of it as a computer program. It's some algorithm. You know, I like to think of it as something you write in Python, so something very concrete, right? Someone hands you a Python program, then the statement of this result says, I can convert this Python program into some non-local game where, you know, imagine that you just ran the Python program, and if at some point the program terminates, then the omega star value of this game is 1. But if your Python program gets stuck in an infinite loop, or you know, it just never stops, then the value of this game is at most a half. And so the first thing we should argue is this implies there's no algorithm to approximate omega star, you know, to something less than a half. Because if you could approximate this value to within a half, you could determine whether an arbitrary computer program halts or does not halt. And this is something we know is not possible. Right, and I'll say a little more about this in just a second, but let's, you know, I mean, we've kind of been alluding to this the whole time, but let's just unravel the consequences. There is no algorithm to approximate this game value. In particular, the algorithm that I described that does the search from below, search from above, it cannot work, which means that, you know, there's a negative answer to Sirelson's problem. Right, so there's some game, like this statement doesn't tell you what game it is, but there has to be some game G such that omega star G is different from omega co. So that's pretty interesting. And in particular, like for this pure mathematics application, there exists these type 2-1 von Neumann algebras that don't embed into this hyperfinite factor. Right, and you know, and then like you can knock the dominoes to all these other connections to these other areas of mathematics.
So could a C# algebra say something about this W star value?
Right. So fortunately, all of this does not depend on your choice of programming language. It's all, you know, Turing equivalent. Okay, so just to sort of like prime ourselves for like how we should think about this, I'm going to quickly go over the proof of why the halting problem is not solvable. Probably many of you have seen this already, but I think it'll be helpful to just review. So the halting problem, right, it's just to determine whether a given computer program halts or not. So you're given the description of a Turing machine, M, determine whether it halts. Okay, so there is no algorithm A to determine this. Right, so, and we'll prove this by way of contradiction. You know, suppose there was, then we're going to create a self-defeating algorithm, you know, that creates a contradiction. So I'm going to call this algorithm B. So what does B do? It's going to run this supposed halting solver on input B. Okay, so in particular, it's going to run it on its own source code. Okay, and first, you know, if you haven't seen this before, this might seem kind of suspicious. Like, how is it possible to run another program on yourself? All right. It turns out that it is. Like, you can actually do this. And you know, if you're curious like how this is possible, you can Google something called the Quine. Right. So these are examples of computer programs that print out their own source code. And if you've never tried something like this before, it's actually kind of tricky. So it's a fun logic puzzle, but it is possible to create these things. So in particular, this step one is well defined. Like it makes perfect sense. Like in any programming language, you can do this. So you're going to run this halting solver A on input B, and supposedly it's going to tell whether B halts or not. But we're just going to do the opposite. Okay, so this is our computer program B, and you know, let's think about whether B halts or not. So you know, you say, well, suppose, like, you know, for any algorithm, it is just you know, a God-given truth whether it eventually halts or not, right? It's like a well-defined truth. So for B, let's say it's supposed to halt, but sort of by construction, it will say, well, I'm told I'm supposed to halt, so I'm just going to do the opposite. I'll just get stuck in an infinite loop. Whereas if A says B never halts, then I'll just stop immediately, so I actually do in fact halt. And so you see there's a contradiction both ways.
Could it be circular that B is defined on A? Like, shouldn't that not be allowed in your proof?
Well, yeah, I guess, well, B depending on A is fine because B and A are separate algorithms. But like I mentioned, you know, you could be suspicious of the fact that B is calling A on itself, but this is a legal thing. You know, you can program, you can write a computer program that does this.
Because I mean, computer programs are just like strings of characters, right? So it's basically you're saying you give it the string of characters that make up the program as input. And so like any program is going to be a finite string of characters. So you can just give it that string of characters as its input.
Right. I mean, but it's not 100% obvious because like, you know, how would, if you were to like write this naively, you would say, well, input my own like string of characters in this, but you can't like continue expanding out. You have to do something more clever to make that work out. But yeah, basically it comes from what Hugh just said. Okay, so now this is like a kind of a cute logic proof, but you notice that there's this element of self-reference, right? Like you have a program that's talking about itself. And this is how you prove that the halting problem has no algorithmic solution, right?
Outside of this class of algorithm for B, could you say that halting problem is solvable?
So certainly, there's lots of algorithms for which you can look at and analyze and try to deduce whether it halts or not. But what this argument is saying is that in general, you cannot hope to solve the halting problem for all algorithms.
Right.
Would this mean that like does this not does this not rule out a algorithm that let's say solves the halting problem but also could also never halt?
So in what sense do you mean solve? So
like if A were a run on itself, it will never halt. As in like it will never, if A runs on itself, then it will never say whether the input halts or not.
Well, we don't know. I mean, this algorithm A doesn't exist, like we just proved it doesn't. But I guess part of the proof says, well, assume that it did exist, and in particular, assume that A halts on all inputs. So presumably if you ran A on itself, it would say, yeah, I halt.
Okay, then.
But you do point out something which is like, in some sense, if if you wanted a semi-algorithm to solve the halting problem, you could. And that algorithm is very simple. Just run the program and to see if it halts. If it doesn't halt, you just keep on running forever. And in that sense, you've kind of like semi-solved it. Okay. So with that like primed in our heads, let's see how how do we take arbitrary programs and embed them into non-local games? And this comes through a tool called compression of non-local games. We're going to use this idea of taking non-local games and kind of like just compressing them in a way that we can encode computations into them. But before that, I'm going to have to do a little more setup. So to sort of make this work out, like we need some way of talking about games in terms of algorithms, right? Like we need some kind of like unified language. So this is how we're going to do it. Let's say that cursive G or curly G is an infinite family of non-local games. So it's not just one game, but an infinite number. So each Gn is going to be some non-local game that has its own question and answer alphabets, has a question distribution, some decision procedure, right? So for every n, there is such a non-local game. And now how they're all going to be related via a single Turing machine. So, this thing, I'm going to call it a uniform game sequence. So uniform because there exists a Turing machine, V, just a single Turing machine that implicitly describes all of them at the same time. Okay, so this V, you plug in n, it says, okay, here's how the nth game works. And what does this description look like? It's going to tell you the sizes of these question and answer alphabets. It's also going to give you basically a recipe for how do you sample from this question distribution. So this recipe will be in the form of another computer program. And it'll give you this other computer program, dn, that computes this decision procedure. Okay. So you can think of it this way. Like you say, I'm interested in game number 100. So I'm going to go up to this Turing machine V. I'll plug in 100. And V is going to spit out a bunch of data. And this data will be everything I need to know in order to execute this game. So imagine that I'm the verifier, and I'm playing with Alice and Bob. Given this description, I can use this S sub n to choose my questions at random. Right? So I'll run this Turing machine. It'll help me choose these questions X and Y. I send the questions X and Y to Alice and Bob. They give me answers A and B. And then to figure out whether they win or lose, I'll just plug all the questions and answers into this D sub n Turing machine, and it'll tell me whether they won or not. Right? Okay, so it should be clear that this V tells you everything you need to know about this sequence of games. To make this kind of meaningful, we also have to insist that everything's computable efficiently. So everything has to be computable in polynomial time. Right? And this includes running this Turing machine V, right? To get the descriptions, I have to get the description in some reasonable amount of time. So poly n time. Once I get the descriptions, when I execute the game, like sampling the questions and deciding whether they win or lose, all of that has to take polynomial time.
Why? Why is it not enough for this to be computable?
Good question. I mean, a priori, you don't have to insist on this, but in this compression argument, we're going to actually have to keep track of how much time things take. And it gets,
okay.
It's not so important whether it's polynomial or something, but just we just have to have a handle on what the complexity is.
So Sn, I guess, would have to be a Turing machine with access to random bits, right?
You can think of it that way. I mean, I haven't exactly said, how does it tell you how to sample? But you can imagine that it's some useful way of sampling from it. So yeah, you feed in random bits and it'll generate a sample. Yeah. Actually, we won't talk about this today, but in the proof, Sn will tell you more details about the distribution that'll be helpful. It's not important for now. Okay, so that's one setup. We have a way of talking about, oh, sorry, was there a question?
Yeah. I was wondering, just going back to the halting problem for a second. So it's kind of confusing me. If you ran an algorithm, or is it even a legal algorithm, one that basically says if, and then some statement that is a contradiction, is neither true or false. If this statement, then go in an infinite loop, otherwise halt. Something that wouldn't even either halt or go into an infinite loop, it wouldn't be either of those options because it's saying something that is neither true or false.
Right. So I guess here we're playing this game, which is proof by contradiction. So we're assuming that this algorithm tells you a well-defined answer. Like it says, outputs 1 if it halts, outputs 0 if it doesn't halt. And we're guaranteed that, by assumption, this algorithm A will always output 0 or 1, regardless of what you ask the algorithm. So this if statement is well-defined, right? Like it either outputs 1 or outputs 0. And depending, if it's 1, then I'll do something. If it's 0, I'll do something else.
What about like an algorithm that outputs 0, 1, or 2 if it's impossible to output 0 or 1?
Oh, sure. So that's, well, you could say, I think it won't be so important for this argument. Like you can say, if it outputs 1, then go into infinite loop. If it doesn't output 1, if it outputs anything else, 0 or 2 or 3 or whatever, then halt. And you still run into a contradiction.
Okay, thanks.
Yeah. Yeah, I mean, this halting problem proof is one of those things, like it's simple, but you could just kind of have to dwell on it for a while. Yeah. Just wait till you see how we use the compression theorem, which we'll get to in a second. Is everyone good with like this V and describing this infinite sequence of games? Hopefully it should be kind of intuitive. It's just some way of describing an infinite family of games. Okay, I just need one more piece of notation. And this is going to be something called the entanglement lower bound. And so this is, you fix a non-local game G, not a family of games, but just a single non-local game G, and you fix a probability P. And this E of GP is going to be a number. It's the minimum dimension D such that using a D-dimensional strategy, you can win in this game with probability at least P. All right. And if there is no such finite dimension D, then we just define this number to be infinity. Okay, so it's just saying, it's just measuring like what's the minimum size dimension you need to win with any particular probability. So, for example, let's take our favorite CHSH game. What are the entanglement lower bounds? So for 3/4, what is this quantity?
0.
0, yep, because you don't need any entanglement at all. You can just use a classical strategy. What about this cos squared pi over 8? This is
1.
1 or 2. I mean, technically it's 2-dimensional, but
okay. Oh yeah. True.
Yeah. And for 1, this is going to be
infinity.
Infinity, yeah, because I mean this is Searlson's bound that we saw a few lectures ago, right? There's no probability 1 strategy. Okay, so that should make sense. All right, so now for the heavy hammer, this is going to be really like the main technical thing. Let's see the statement of the compression theorem. So this is going to give us a procedure for compressing an infinite sequence of games into another infinite sequence that is compressed in some sense. So here's the statement. There exists an algorithm C for compress, that takes as input Turing machines or algorithms, and outputs Turing machines. Okay, with the following property. All right, so the way I like to think about it, it's really this box, and in comes, a Python program, and it'll do some crunching, and it outputs another Python program. Right. What are these Python programs? So let's say that, let's call them V and V prime. V is going to specify, V computes some infinite sequence of games in the way that we just described. Right, so suppose that you gave this V and it describes this sequence of games. Then it'll output another V prime that computes another sequence of games. I'll call it G1 prime, G2 prime, etc. And now I have to say, how are these games related to each other? For all n, if omega star of the n plus first game of the original sequence is equal to 1, then the nth game of this compressed sequence is also equal to 1. Right, so in some sense, this compression procedure preserves perfect winning probability. And the second thing is we have a relation between the entanglement needed to play this compressed game with probability 1/2. It's at least the greater of either the entanglement requirements for the n plus first game of the input sequence, or n. So I think it's worth just staring at this compression theorem for 30 seconds and try to digest what's going on. There's a lot of moving pieces.
I can see why you want the first condition, because you will construct a series of games that if the Turing machine halts, then from this point on, the probability to win will be exactly 1, and then you just compress again and again and again and again. But why do you need the second condition? I'm not seeing.
Well, we'll see in a sec, but
okay.
I think, yeah, you're on the right track. Yeah, so I think the salient features are, first, it's a transformation from a sequence of games into another sequence of games, such that, the second sequence is related to the first in this kind of shifted way, right? We have this, the nth game of this second sequence is related to the n plus first game of the original sequence. And we have this, somehow the whatever entanglement you need for this second sequence is related to whatever you needed for the first sequence. Yeah, so before I move on to show how this is used, any questions about the statement? Okay. So we're going to use this to, right, I told you that the statement was I can take any Turing machine and map it into a non-local game G sub m with the, that can tell apart whether it M halts or not. So let's fix this M, right? We're going to define a uniform game sequence that depends on M. And the way I'm going to describe it is to use, some bit of pseudocode. So this is how the nth game is going to work. So this is it's just some informal description of how the game works. So imagine that you're the verifier in this nth game, right? So as the verifier, before you even talk to Alice and Bob, you're just going to take this program M and you're just going to run it for M time steps.
When you say verifier for the game, you mean like the decision procedure D?
Yeah, I mean, like the combination of the sampling and the decision procedure D.
Okay.
Yeah. Yeah. Okay. So you're going to run M for M time steps. If M halts in this time, you say great, except. So here, even before you've even talked to Alice and Bob, you say, well, you automatically win, right? I don't even need to send you any questions or answers. Go home and enjoy. But suppose that this Turing machine doesn't finish in this time, then the verifier is going to do something more elaborate. It's going to run this compression procedure C on V. Now what's V? V is supposed to be the Turing machine that computes this sequence. And you might start getting a little weirded out by that, but we'll deal with this in a sec. V is a Python program. We plug it into this compression procedure C, obtain V prime. Okay. So now we're able to play with this output sequence. Run V prime on N to get a description of G prime N, some other non-local game, right? And then since we know everything we need to know about this game, we'll just play G prime N with Alice and Bob. Okay, so so I've just written some pseudocode down. The first thing I want to try to convince you is that this does describe a non-local game, right? Because you can imagine that the decision procedure of this Gn will sort of carry out all of these computations, right? It'll run this M, it'll run the compression procedure, and when it gets this description of G prime N, it'll just do that. There's this funky thing where in describing G prime N, in describing this Gn, we're we're saying run this compression procedure on V. What's V? V is the thing that's defining Gn, right? So there's like some circularity going on. But it's the same kind of circularity that went on in the halting problem proof, right? I claim that this is okay. Like we don't have to worry about it. It's well defined. Like this all can be set up in like a self-consistent way. What else? Yeah, and so, you know, basically the fact that I've kind of written out this pseudocode for you, like it's basically like the pseudocode of V. Like when you run V, it'll output this description that I've just written down for you, right? So you can imagine that this is all possible. The other thing that I want to convince you of is that this sequence of games is all computable in polynomial time. Right, so let's just do an accounting of what's the time complexity of each game Gn. Right, so step one, you know, takes n time steps, right, by definition. Right, we're just running this program M for n time steps. Step two takes O of 1 time, a constant amount of time, right? We're just running this compression procedure on V. V is some fixed object that doesn't depend on n at all. And so when we compress it, it just takes some amount of time, but the important thing is it just doesn't depend on n. V prime, you know, sort of, we're guaranteed, since it specifies like a game sequence, it runs in polynomial time. Also, this compressed game, G prime n, it's also going to be polynomial time. This is by definition of uniform game sequence. Okay, so, you know, we add all of this up and we get a polynomial time computable game.
Why can you necessarily run C on V? Because doesn't like being able to run C on V depend on V being one of these, like an algorithm that computes these kinds of game sequences, but only computes these game sequences if you can actually run C on V?
Yeah. So you can sort of set it up where like you know, you first define it so that no matter what, all of these games Gn will be well defined. Like, so V will actually exist. And so once you've set that without relying on any other assumptions, and then once you've set that up, then you know that once you run C on V, it's actually it will output another proper game sequence. Or
like,
you know, maybe
so you find like a V prime prime, and then you define V based off of this V prime prime, for example.
Something like that. Yeah, you can do it that way. I guess, you know, at a high level, this property of being like something that outputs a uniform game sequence, this is just a syntactic property. You know, it's not something that you have to like run the Turing machine in order to find out whether it outputs a game. It's just no matter what the way the Turing machine is set up, it always outputs a description of some game.
Sure. Yeah.
Yeah.
So, depending on the definition of that G game, is it possible that if when you carry out your compression, that you can lose a lot of information on your V, and that your V prime is not going to approximate V very well, especially if it has a lot of values that are is called the expected tensor, is above the max value there, max of expectation and n, that therefore C could, there's a class of V definitions that C could not be an optimal transformation to carry out on. I hope that makes sense.
I didn't quite follow, but I guess the only thing that we'll use about this compression theorem are these two items that I've written down.
So if the item of where you have the max there, if the item on the left is very large compared to the say n value, sorry, the item on the left hand in the max is going to be much greater than n. Could you wind up, and you have a lot of those values, could that then wind up with lots of information?
So I don't know what you mean by loss of information, but you know, all we know is just this this bound. So it could be smaller than n or greater than n, but we just know that it's going to be the max of the two.
Oh, okay, I'll ask you after the class.
Sure. Yeah, I think maybe it'll be more helpful if we see how it's used. Okay, so we're going to, so I've just defined some game, and now let's start to analyze it. Subsequence of games. So, you know, we want to analyze omega star of Gn. So let's consider two cases. Let's suppose that this Turing machine halts at some time. So say it halts in time t. Okay. Then for all n that's greater than t, and I think Yuval was alluding to this, like by the way we've constructed this game, the verifier will have enough time to run this program out to completion, right? So the program is going to complete, and then the verifier is going to accept, and you know, Alice and Bob aren't even involved in the game. So the value of this is 1 by construction, right? Hopefully that's clear. So what about n less than t? We have to somehow figure out what the game value is. Well, let's just think about the pseudocode. So this step 1 will never terminate, right? So we're just going to automatically move on to step 2. We're going to run this compression theorem procedure. We're going to get a description of this game G prime n, and we're going to play this game. So this game Gn has effectively become the exact same game as G prime n, because you're just following all the same rules. So in this case, game Gn is, you know, equivalent to G prime n by construction. In particular, they must have the same optimal winning probabilities. Okay, but what do we know about the winning probability of G prime n? If you remember from the compression theorem. You all were about to say something?
Who?
Yeah, I think you had it earlier. So.
Oh yeah, like it will be 1 if the value of the prior game in the original sequence was 1, but you will just do that again and again and again and again until you reach t, and then it will be 1.
Exactly. So you can, you know, so we know that, you know, so we have a kind of like an anchor that omega star GT is equal to 1. But by the compression theorem, that must mean that G prime of t minus 1 is equal to 1, right? So this is by the compression theorem. And then we just kind of like ricochet down for all n. right? And so that implies omega star of g t minus 1 without the 1 is equal to 1. And then, we just sort of carry out this game right? And so we just deduce that for all n, this game must have value 1. Right? This comes from using the compression theorem over and over again.
Okay, so maybe this is the thing I'm not seeing. Why does the second arrow hold? Like the one that goes down.
This one?
Yes.
Oh, this comes from this statement. So this comes from this equivalency.
Yeah. Sure. Thank you.
Can you say again why that statement is true? Because I'm missing that point. Why are the games equivalent?
Oh, they're equivalent because we're asking what is the maximum success probability of Alice and Bob in this game. It only depends on the questions and answers, like the decision rules and sampling of the game, right? And what game is being played with them? It's this G prime N. Like this is all that really happens in some sense. Like steps 1, 2, and 3 are all just like happening behind the scenes in the verifier's head.
Wait, but okay, so in step 1, if we accept, then it's over, right?
Mm-hmm.
So omega star of GT would be 1, but GT never plays Gn prime.
Mm-hmm.
So wouldn't that not be equal by construction then?
Oh, yeah, I was, this by constructions, we're considering n less than t. So assume n less than t, then we have this equivalency. So like say n is less than t, then step 1, like you can just imagine like you always just pass over it.
Okay.
Ariel, does it make sense now?
Yes, I think so. There are a couple points I need to think more about, but I don't have like questions.
Okay, so it's sort of by the way we've set up this game, that's why we have this equivalency.
Yeah, the earlier question I asked, I'm clear on. So thanks.
Okay, cool. Great.
So the second condition you need for soundness.
Yes, so right, so we're done with the m, like if m halts in time t, then in any time, then we know all of the games in this original sequence, G1 up to G2, G3, and so on, they all have value 1. Okay, so we're at least good on that front in the halting case. What about the non-halting case? And this is where this entanglement lower bound comes in. So suppose that it never halts, right? What's going on? So again, we have this equivalency between Gn and G prime n. So for all n, these two are equivalent games by construction. And looks like you've all had a flash of realization. But you say, well, okay, well, let's think about omega. Like we really want to show what omega star Gn is, but how do we relate it to, okay, so we know that this is true, like just by the same reason. But we can't really do anything with a statement because we can't relate this to I mean, we know by the compression theorem it's related to Gn plus 1, but then what's Gn plus 1? And like we're kind of like stuck in circles. But this is where we use this entanglement lower bound. We also know that these two must be equal, right? Because they're the same game. But the compression theorem tells us something about G prime n. It says that whatever entanglement you need, it has to be at least the entanglement you need to play the n plus first game in the original sequence. But since Gn plus 1 is equal to Gn plus 1 prime, these have the same entanglement requirements. And this is bigger than Gn plus 2, right? And maybe you can see where this is going. Okay, so we have like this infinite chain of greater thans. So what do we conclude? That whatever entanglement you need to play this Gnth game, this has to be greater than Gm prime for all m. Okay, but remember that this entanglement lower bound gave us a max. And we also know that Gm prime has an entanglement lower bound of m. So you put the two together. So this comes from the max. So you put the two together, and this implies that entanglement of Gn to win with probability a half is greater than m for any m you choose, right? So there's no finite lower bound on this entanglement, right? So this implies that the entanglement needed to play this game with probability a half is infinite. And it tells you that there is no finite dimensional strategy that can do better than 1/2. What does that mean? We can actually deduce something about this optimal winning probability. It has to be at most a half. Okay, so we're basically done. We've shown that if m halts, then for any n, this is 1. If m never halts, then this is at most a half. And so we can complete our reduction by saying that someone walks up to you with a Turing machine M, you can just produce the first game of the sequence, and it'll have the properties that you want. And so that completes this MIP star equals RE conclusion.
Well, you did not show us how the compression works.
Yes, that'll be for next time. But assuming compression, we can do this basically recursive self-compression. And this is how we encode whether a Turing machine halts or not in a non-local game. And it's 6 o'clock on the nose. Yeah, next time we'll see how you prove this compression theorem.
Wait, sorry, maybe I missed that. So what is the precise connection between the complexity class MIP star and the problem of approximating omega star? It's complete, or like, did you mention this?
I think I glossed over it. Yeah, basically, it's a complete problem for MIP star.
And why is that?
Good question. Well, I guess there's different answers to this. Okay, so the first answer is that approximating the value of a non-local game is contained in MIP star. And we've just shown that you can, you can reduce RE, the halting problem, to this. So that kind of like shows that this is and then RE contains MIP star. So it sort of gives like a matching upper and lower bound. There's a different way of looking at it, which is given an arbitrary MIP star protocol where, you can have many rounds of interaction and, many provers. It turns out you can always transform that into a non-local game with just two provers. With just one round of communication.
Oh, okay.
Yeah.
Wait, so which one is the strategy that you follow? So it's the one that you describe here? I mean, in your proof?
Yeah.
And do you also describe the other way of doing it?
Oh, the other way of doing it, that way just shows that the game problem is complete for MIP star, but it doesn't show a lower bound.
Thanks.
Yeah, but I won't be talking about that.
Even if the MIP star protocol has a number of communication rounds that depends on n, you can still reduce it to just like 1, 2, and that's it.
Mm-hmm.
Wow. Okay.
Yeah, it uses actually a lot of the stuff you've seen in this class, like rigidity and the Hamiltonian problem and so on.
Who proved this round reduction result?
The first paper to prove is by Jiangfeng Ji, and then we had a follow-up paper that kind of simplified it a lot. But I think Jiangfeng was the first to prove this. I guess the issue with that though is this round reduction increases the number of provers. I mean, by a constant number, but it still, you don't get it for free.
Is this also true for QIP? That is that like each, you can just reduce it to 1, 2.
Yeah.
And that's it. Oh. And this is not known to hold classically, right?
Classically, it is true that all MIP protocols are convertible to, 2 prover 1 round. This is also known.
Or all MIP protocols.
Yeah.
But not all IP protocols.
No, that we don't think is possible.
Oh.
I have another question about the halting problem.
Mm-hmm. Yeah.
I'm wondering because B has this sort of property that like if B halts, then B goes into an infinite loop and vice versa.
Mm-hmm.
I'm wondering if you make like a promise to only include like algorithms that don't have this sort of contradiction in them. So like B halts if and only if it doesn't go in an infinite loop, then would there be something that could tell you, an algorithm, a halting algorithm?
I think the tricky part there is like formalizing what it means for an algorithm not to do something tricky like that. I think it's just really, really hard to get around this style of halting contradiction. If I remember, there's something called Rice's theorem, which shows that, anyways, you can Google Rice's theorem. I think it might answer your question. It sort of says that, it kind of says, yeah, you can try to institute all sorts of different properties, but a lot of them will end up being undecidable. Maybe someone who's taken a computability class more recently can say more.
Like in general, most properties are indecidable.
Yeah.
Like, I guess my sort of intuition about this, and I haven't taken any course like this, but my intuition is like we humans can like look at these problems and figure out when like it would not be able to, like it doesn't have either a halt or not halt. So like there's some algorithm running in our brains, right? But maybe there's ones that we couldn't even figure out before.
Yeah. I mean, I think, you know, not to put down our own brains, but I think we just haven't looked at that many. Actually, you know, but if you've debugged any program, it can be really hard to figure out whether something halts or not.
I would say just like on that point, I don't like his ideas. Like I would say I disagree with what he says, but Roger Penrose actually says like the human mind is like exactly in this way capable of, you know, mathematical insight and can see the solutions to things that are uncomputable. And he has like his theory of, he had whatever, he wrote like books about this, one of which I read, which I don't find convincing, but like he argues, he does argue that, and you know, like Roger Penrose deserves consideration, I guess.
Cool.
Yeah, I think it's definitely worth, yeah, it's an argument worth considering. But I think, you know, even in practice, you know, I don't know how much software debugging Roger Penrose has tried doing, but I think, you know, in general can be quite difficult. So at least from experience, I believe the halting problem is unsolvable.
I have a very basic question about the definition of compression. So I'd asked you earlier in the lecture, this was the entanglement property there, the entanglement step. So you have a max there, and the choice of the cap of n. Is there any specific reason why it's n? Oh,
you mean this thing here?
Yes.
Oh, so it doesn't really matter what this is. It just needs to be a growing function. Like we never use the fact that it was n per se, but it just sort of goes off to infinity with n.
Okay, yeah, that's what I was asking about. Okay, so I guess there's no worries about, you know, having a large enough cap in relation to your choice. So the input g of n plus 1 and its entanglement value, like its relationship to the choice of n.
Yeah, it's not so important. I mean, anything that goes to infinity would make the argument work.
Okay, and just a point. Other question I'd mentioned was about that some guy in Waterloo here had done a presentation on this the CEP problem, and he was talking about some for these non-local games that you can have this affiliated C star algebras, and that their representation theory can tell you if the game has a perfect strategy or not for each of the possible models. And I was just wondering if that is of any interest with relation to CEP as an algorithm for determining these the winning probability or the optimal strategy.
Oh, I see. Oh, I guess, yeah, I mistook what you said earlier about C#. I thought you were making a joke about.
I meant C star.
C star. I see.
Some guy called Vern Paulson, I think, from University of Waterloo.
Yeah.
There's a presentation on that.
Yeah. I guess, you know, that's sort of like a whole nother thing to get into, but definitely, yeah, there's one of the questions that's remains open from this uncomputability result is, you know, how can we actually get a handle on describing what this, you know, infinite dimensional commuting operator strategy that supposedly does well, you know, what does it look like? You know, can we describe it? And you know, this is something that, you know, the math people are very interested these days. Like we know it exists, but you know, what are its properties? And the C star algebra thing that you're mentioning, I think, is a possible way to try to get a handle on it. But people are trying to figure this out.
Neumann algebra is just special
Okay, thanks.
algebra, right? So
Randy, you're very faint. I don't know if it's like your microphone or something.
Is that me or?
No, I think Randy was trying to say something. Okay, maybe not. Oh, okay. So you're typing it in. Right. Yeah. So von Neumann algebras are type of C-star algebra. All right. So next week we'll dive in and see how you compress non-local games.